Welcome to Breadboarding. In the previous video, we managed to get the IDE Disk Controller installed, and we also made use of a more modern SATA drive plugged into a SATA to IDE converter here. We tried to get that working, but there were a few problems. So what we're going to be doing in this video is going through some of the fixes that I've done and then showing how to boot MS-DOS off hard disk. This is video 24 in the Breadboard PC 8088 version 2, and this is part 2 of the IDE Hard Disk and Controller video. So a number of fixes I've done, so I'm just going to come back to this just to guide me through this. So the first thing I had to do was to clean up the wiring of the ground 0 volt rails between the various breadboards and the bus rails. And this is what we saw in the previous video. So the CS3 and CS1 signals are kind of the main drive select signals that go out to the IDE hard disk, and you can see from the previous video the oscilloscope here showed that we're getting quite a bit of interference on those signals, and also that the logic analyzer was showing multiple blips on various signals around this sort of time. And then this is another similar trace, and you can see the interference on some of these signals here mean that we weren't going to get much success. So what I've done is I've actually rewired a lot of the breadboards and things and made sure that all of the ground or earth connections are all a bit more consistent and they're all emanating out from a single point on the CPU board. And now this is what the CS1 and CS3 signals look like. You can see from the oscilloscope here that there's a lot less interference. There's a little bit of bounce at the beginning here, but that's well within the acceptable limits. And then if you just compare the old signal with the new signal, you can see that's quite a lot of difference. This is the CS1 to the IDE drive before and after the rewiring, and similarly for CS3. So that seems to have improved things quite a bit. What I thought is I've gone through and fixed quite a number of things that had kind of been intermittently occurring. So sometimes the Breadboard PC wouldn't reset cleanly, so it would come up and perhaps the LED display would get stuck on a particular digit. And I've rewired some of the breadboard connectors coming into the board and put them in some different holes because sometimes there were some loose connections, sometimes causing problems. This is just an indication of what was going on. So this is the logic analyzer from coming out of reset. Now normally the 8088 and 8086 processors will look at the address FFF0 for the first instruction. You can see here that in fact this one has found the instruction EA from the first address here, but it hasn't actually changed on the next address. We can see that there's a C0 and F0 here, but in fact the address that it then actually tries to execute is not correct. And if you look down the bottom here, the address A0 line is not changing between these values here, so it looks like there was a problem actually on the wiring going to the EPROM there. So although the address line there on the main bus rails was okay, the address line on the EPROM wasn't quite right. So I've rewired that, and that seems to have fixed that particular problem. And this is then what it looks like when it's working correctly. You can see that the address lines there is toggling, and in fact that we've got EA00C0, 00F0, and what that results in is that we get the correct jump. So we actually jump to the monitor starting at C000 there, whereas previously we had it jumping to a rather random address there. Now there are also some problems where we're getting data corruption as well. So as part of the initial loading of the monitor, so you can see here it starts at C000 over here. Around this sort of point, we're actually getting the incorrect data being read and loaded. You can see down here that this particular instruction here should have been loading. This is in fact 36 plus 9000 offset, so this should be in fact C6 when it appears on the bus here, just because the listing doesn't include the 9000 offset. And in fact then when this rewiring was fixed, then in fact what we got, you see here that the listing has B736, which is least significant byte first. So this in fact evaluates to C6B7, and what you can see here is we've got the B7 and the C6 there, and it's now been written correctly. So there's some problems that when it was coming out of reset, and sometimes when I was interrupting the running the operating system like the BIOS or MS-DOS, it was actually not working correctly, and this has actually resolved that particular issue. So there's another issue fixed there. Also, sometimes keyboard input would just sometimes hang on boot. And as I investigated this, it's quite a tricky one to get to the bottom of, but it turned out to be the interrupt acknowledge lines. The wiring on it was quite long, and sometimes interference or blips occurred on it, and this would actually cause quite an unusual set of circumstances to occur. So this is the output of the logic analyzer, and you can see down the bottom here we've got our two interrupt acknowledge pulses. Now, the way how the interrupt controllers and the interrupts work with the 8088 and 8086 is that when an interrupt occurs, the CPU will actually indicate the interrupt acknowledge signal twice, and on the second signal, what the interrupt controller should do is output to the data bus the offset to the interrupt. Now, it just so happens that the timer interrupt 0, has an offset of 08. But what you can see here is, if I just zoom in here a little closer, what you can see here is that during this first interrupt acknowledge, there is a brief blip here. And what actually happens is that the interrupt controller senses that blip and actually starts to output the 08 a bit too early. So it's actually before the start of the second interrupt acknowledge pulse. And the problem that then occurs is at the end of this second interrupt acknowledge pulse, that in fact the data bus has now gone to FF because the interrupt controllers stopped driving the bus. And what that results in is that the interrupt that the CPU thinks it needs to handle is in fact FF. And in fact, if we actually just do a quick calculation, what the CPU does is multiplies the interrupt vector provided here by 4 to find the actual address that it uses. And if in hexadecimal we do FF times 4, we end up with 3FC. And in fact, what we can see is that the CPU looks for the address at 3FC. Now, it just so happens that when the BIOS starts, because the BIOS data area is at 400, the first 1K of RAM is actually used for the interrupt vectors. And because the top interrupts are never used, then in fact what the BIOS does is uses the 3FF downwards as the BIOS stack. And in fact, there's actually on the stack is in fact that address there. And when I was looking into this, this was actually getting quite confusing because it looked like it was basically restarting the BIOS again or whatever. And in fact, when I actually looked at what those addresses were, so if we actually look at the address there, 3FC, you can see that when it's loading the address 3FC, we had 3B E2F000. So that address is in fact F000 E2 3B. And if we look at our listing here from the BIOS, we do have to remember that when we look at the addresses here, we have to add 900 to them because this is the offset that the code uses into the ROM, which does tend to make things a little more tricky. But if we look at what 523B plus 9000 is, that's E23B. So in fact, the address that's stored on the stack here is in fact the return address from calling the video BIOS initialization. So this is something we looked at a few videos ago. So when it finds a video BIOS, in particular the VGA BIOS, what it does is puts the address at 67 hexadecimal, so it'll be 4 bytes there, does a call far, which will then go off and call the video BIOS, and then when it returns, it will then return back and start executing here. But because we've picked up that address accidentally as part of the interrupt vector, then in fact what it does is actually starts executing the BIOS from this point in here. So when this interrupt occurs, rather than handling the timer correctly, what it then does is actually goes off and starts the BIOS again, which is likely to result in problems. So what we've done there is rewired the interrupt acknowledge signal, and that now is clean. And what I also covered in the previous video is to try and get to the bottom of some of the problems. I actually dug out the project I did previously, the Breadboard PC version 1, and this used an Intel 8288 bus controller. And what I did is control the signals between the version 1 Breadboard PC and in the version 2. Now in the version 2, we're actually taking a lot of these signals straight out of the ATC 8088 processor itself, so we weren't using the bus controller here. And what I have done is gone through and compared a lot of those signals. And in fact, there was one signal which I thought perhaps did need to be addressed. The address latch enable signal in the version 2 of Breadboard PC was about 20 nanoseconds longer. And we can actually reduce that by ANDing the address latch enable with the inverted CPU clock, which I'll show you in the following slides. So this is the output from the Breadboard PC version 2. This is when it was running at the basic speed, so not the turbo, this is the standard speed. You can see here the period here is about 210 nanoseconds per clock cycle. When we're looking at the Breadboard PC version 1, I did have to overclock this slightly. So this was basically 16 megahertz divided by 3. And so you can see here the period here is 190 seconds. So the periods here are slightly shorter. And then if you look at the memory write signal here on the version 2, we can see that these lines here are coming down for every clock cycle. You can see that this is just about 2 clock cycles for the write period. And if we then look for the version 1 Breadboard PC, you can see that in fact the 828088 has 2 signals. There's the basic memory write, but there's an advanced memory write. Now it's actually the advanced memory write that the original PC uses, and you can see here that this signal is in fact 2 clock cycles, so that looked to be okay. I've done the same with the IO read, IO write, memory read as well. So I was then having a look at comparing some more signals between the version 1 and version 2, so the difference between using the bus controller and the native 8088 signals. And we can see here that in fact this period between the address latch enable and the start of the memory reads, you can see down the bottom here, if we zoom in it might make it a little easier to see. So you can see the address latch enable goes high, that it signals that a new address is available, and then on the falling edge there, then the latches will actually save that. So some of the addresses are actually multiplexed from the CPU. And we can see that this period here is 90 nanoseconds. And if we look down to this one here, you can see this period here is in fact 40 nanoseconds. So it is a fair bit different. Then if we look at the width, so this is the width of the address latch enable. This is the C1, C2, so this is 110 nanoseconds on version 1, and version 2 is 90 nanoseconds. Now if we do a conversion between the clock rates, then by converting the width of address latch enable in version 1 to be the equivalent clock signal here, you can see that it's actually about 70 nanoseconds, whereas the width here is 90 nanoseconds. And if we have another look at the top here, we can see that the end of address latch enable is fairly close to the rising edge of the clock signal there. But if we go down to the other one, we can see that in fact the end of this is actually going almost to the end of the rising clock signal there. So what I thought I could do is, if we actually shorten this address latch enable, it might improve the reliability somewhat. And so what we just need to do to shorten this is if we invert the clock 88, which is this signal up here, so this one becomes high, and if we just AND this one with this inverted one, then that should actually shorten this. So it'll actually come back from being in the middle or end of this clock period, it's going to come back to the beginning there. So that's one of the other changes that I have done. Now, in addition to that, what I've also done is enabled the bus ready signal coming from the VGA card. Now, bus ready, or IO ready as it was in the original IBM PC, is a way for slower devices to actually slow down the CPU and give a little bit more time for accessing slower memory. Now, in order to do this, I'll look at the KiCad diagram. The bus ready, IO ready adds wait states when it goes low, so when it's high then it doesn't affect anything. But the VGA card does actually add wait states. This signal comes out. Now, unfortunately, I couldn't modify the existing programmable logic devices to do this because the bus ready, IO ready needs to preset a flip-flop, and it just so happens that the 750C flip-flops only allow one preset across all flip-flops, so we don't have the flexibility to be able to add it to that particular configuration. So I've ended up having to add an additional flip-flop to the diagram. So this chip here, which is the wait states and speaker PLD here, this has been reworked, and I'll look at what the changes are here. But basically what we now do is, rather than using a flip-flop in here for the ready wait processing, what I've now done is added a flip-flop over here because this is where I could fit it. And what you can see now is that the bus ready comes in from the connector down here, which is where the VGA card connected. It's pulled high by default. So if the bus ready goes low, then this will start to add wait states to the clock cycles. The I/O read-write clock is what clocks this particular flip-flop, and the clear comes from the ready wait asynchronous reset, again from the other side here. And this is now ready wait and output that now goes back into this PLD over here. So previously this PLD was generating this signal, but because we couldn't do the preset high, then this is now actually taking it in, and then this has now been modified. So if a quick look at the changes made in the PLD configuration, this is comparing version 5, which was done in the previous video, with this one. There's been a few iterations of it as I've gone through doing the various fixes. This talks about the various changes that we're doing for the bus ready. We've also added the flip-flop has been added to the schematic. So you can see here that where we had ready wait, then now we've got the bus ready in. We've also now got the ready wait asynchronous reset is now active low, which we need for the external flip-flop. We now have an output signal for bus ready, and I'll explain why we're doing that in a minute. And then the ready wait is now an input coming from the new flip-flop. Then we've got the new pins there. Now the ready wait asynchronous reset is now active low because that's what the external flip-flop requires. And we've now relabeled some of the pins because we needed extra signals for the bus ready signals. I have also put in here some memory refresh logic. So I was thinking originally perhaps the VGA card was not happy because we didn't have any memory refresh cycles. I have tried that, but it doesn't seem to make any difference. I may do another video in the future about how to fully resolve all of the VGA card issues, but I won't cover that now. Now down here, the ready wait asynchronous reset. Previously we were doing it on cycle 4 and cycle 4, and now I'm doing it on cycle 1 when we're not in turbo mode, cycle 4 in turbo. The logic that we had previously for ready wait, which was built into the PLD, is now moved out onto the external flip-flop, and so ready wait is just an input line now. And you'll see that because we've changed the polarity of the ready wait asynchronous reset, then we've needed to include the exclamation mark in the resets there because we want it to be active high. And then there's a few other of the ready waits down here. We're only using up to ready wait 4 at the moment, but I was looking at using the 5, 6 and 7 to address the particular issue that I'll come to in a minute. So these are all the memory refresh flip-flops that I had for producing a sort of fake memory refresh signal. Now the key thing really here is that the bus ready is basically what the bus ready in is, but then we disable it for memory read. So one of the problems that I had with the VGA card is that it would actually leave the bus ready signal low forever, and so that would actually effectively cause the CPU to halt. In fact, under the original PC, the way how DMA was implemented is that it would actually set this sort of bus ready effectively low, and it would effectively cause the CPU just to halt until such time as the DMA controller gave the bus back. But in this particular case, for the moment, what I've done is I've disabled the bus ready wait states when we're doing memory read for the moment, and I'll show you a slide in a minute which shows that. That has all been programmed, and I've changed the wiring on the board. And you'll see here that the VGA card was leaving the bus ready low on the memory read, and that effectively disabled the PC or put into halt, so that has been disabled. And you can see here that this is an output trace, and you can see down the bottom this is the bus ready coming from the VGA card. And you can see it's a bit unusual in that it pulses the bus ready at about sort of 40 nanosecond intervals, but then it basically gets stuck low. And now this bus ready for reads is absolutely fine for hundreds if not thousands of reads, but occasionally just gets stuck, and then the memory read cycle gets stuck in this way, and it basically just goes on forever. So I need to look at this and see if I can improve this. I did put some timeouts in here using Radio 87, but that doesn't seem to have really addressed the problem. So I'm going to need to go in and have a look at that in more detail. But for the moment, the VGA card's working better. It's not perfect, but we will look at some VGA tests as we boot up the Breadboard PC. So then we come on to the PC IDE disk controller. So I covered this in the previous video. So it's based on XT IDE Rev 4 design with a swap out of 2 chips for this 646. We're running it in the Rev 1 mode, which is a bit slower than the faster mode. We've already configured the XT IDE BIOS, and we've added that into our BIOS starting at the 800 range. We've also moved the main BIOS already up to F9000, and we've also configured the BIOS to look for extensions going all the way up to F9000. So this has now all been done, made ready for us to try and boot up the operating system from the hard disk. Now, rather than using a blank hard disk, I'm just using one that I used in the previous series. So this should already have MS-DOS on it, and it probably has most of the things from the previous series already installed on it. So I'm just going to switch to VGA capture, and then we'll have a look and see if we can run this up. We'll run a few programs and perhaps test the video output using one of the test utilities I've come across. So you can see the video BIOS. Now, as you found a disk at master, there's no floppy disk in the drive, and then it's booted off C. So you can see there that we've got MS-DOS version 330, and it's booted off the C drive. Now, one of the problems that we've still got is that the scrolling of this is still problematic in that when it scrolls, then the reading of the video RAM is quite erratic. However, if you do a clear screen, then we can actually do things quite comfortably. That's something I'm still looking into. Now, what I will just do is to show you some of the test utilities that I've been using for this. So one of the ones is disk test. So this was one that I ran previously, and if you remember from the first part of the series, there are a number of errors coming up. So there are exclamation marks coming up actually with this disk test. So I'm just going to run the disk test. I'll speed it up because it takes about 8 minutes or so. And then when it's finished, then they'll come back and they'll look at testing the video card. Disk test, media test. Okay, so that has all passed. Took 8 minutes, 19 seconds. No blocks had errors. We compare that to what we had from the Breadboard PC version 1. This is the slide from the introduction, the first video of the series. You can see here the exclamation marks highlighted in red show where there were errors. So you can see that quite a few errors were found here. So that's looking good. Okay, so what I'm just going to do now is to have a look at testing the video card. This VTDFR45 is a really good VGA test program. I'm not going to go through all the tests in here because there's a lot of them, but I'm just going to go through so we can actually check to see that the majority of the VGA card is working. We'll also highlight a few of the areas that any of the tests that require reading memory then rewriting it then tend to have some sort of glitches on it. So if just look at the color bar menu first. So I will not speak over all of it. I'll speed it up a bit between some of these. 1 or 2 take quite a while. So again, I'll speed those up quite a bit to get through all these. This is one that, in particular, before I did some of these changes, then this had quite a lot of mess all over it. The fact that this is coming out clean now is a lot better than it was earlier in when I was testing this. This was one of the ones that indicated the problems reading and then writing. So particularly if it's setting a pixel and it reads the existing byte and then sets a new pixel, then this seems to be the cause of this type of problem. Again, this stripes requires the reading of the video memory for writing pixels. Again, seems to suffer from this problem. Then we'll just do a few from the crosshatch menu. There are one or two options on here which do take a while, so these will be sped up. This is one of the quicker ones. You can see there's a few pixels where we've not got white or we've got pixels missing. And this has a few missing lines, but it's generally okay. Again, it's mainly writing, so it doesn't seem to suffer many of the problems. Now some work better than others. I'll just show a few of these. This multiburst one shows where there are problems reading the existing video RAM data. And at the end there, it does seem to overwrite some of the data there, so it wasn't quite perfect. And this should be a very fine matrix of squares with this pattern overlaid on it. You can see there that there are some areas where it's not quite coming out right. Now, one of the interesting things here, it also has tests for CGA and EGA. So I have gone through most of those, and a lot of those come out okay from this. I was just going to go into one further test. The CT was one of the test programs I used earlier in the series. And if we do some of the graphics tests here, it's interesting in that when it uses the BIOS to update the screen, then we get the interference problems, but when it's using direct writes, then in fact it's a lot cleaner. You see the direct writes doesn't have any interference at all. The direct writes are okay. So it would indicate there's probably something to do with the BIOS routines which are actually updating the screen, maybe somewhere to look into. So I'm going to carry on looking into that. This was one of the outputs of the test program, so I wrote some test software to specifically poll the status register and try and read the identified device data. So this is an output from early on in the process where you can see that the data here does not look particularly encouraging. And then a later version, this is where it's now actually working properly. And in fact, it's actually dumping the drive identity information. This information was pretty consistent with what I got from the version 1 Breadboard PC. This output here came from the version 1 Breadboard PC, and I've compared all of these bytes here, and it's pretty much identical. So it looks like things are actually working pretty well now. There's a few problems to look at with the VGA reading video RAM. So I've just about come to the end of the Breadboard PC version 2 project for the 8088 processor. So I've been able to show getting MS-DOS 330 running off the hard disk. I was using the hard disk that I used from the previous series. And so what I'm going to do in the next video, I'll start off by taking a blank hard disk and partitioning, then formatting it, installing the operating system. Then we'll try and get the PS2 mouse working and then run Windows 1.0 initially. And then we'll run later versions of Windows as time becomes available. and we may need to do some configuration around getting the early versions of Windows working with the VGA card, although it should theoretically work in CGA and EGA compatibility modes. So if you don't want to miss out on future videos, then please hit subscribe, and if you could hit like as well, it just helps to make the videos available to more people. Thanks for watching.